All right, are we live? I guess we're live. I don't know what I was doing. Okay, so we're going to start today with introduction to welding. We're going to dig through Steelworker, United States Navy Steelworker Manual 14250. We're going to do chapter 2 today. We're going to talk about basic heat treatment. If you get a chance, visit my website, or a website that I've been dealing with, train-eng.com. For PDHs, we got a couple of CWI courses on there, some other material. Give it a look if you're looking for a reasonable program for taking the CWI exam. Sorry, I can't talk today. So anyways, let's talk about heat treat today. So welding and cutting or even grinding on metal produces heat, which in turn has an effect on the structure of the metal. So if we're dealing with welding, a lot of the time, this is things you need to know, because at some point you're going to come across the terms for preheat, post-weld heat treat. Does it need stress relief? Does it need to be annealed? Does it need to be normalized, quenched, and tempered, whatever? So that's the basics of this little chapter here. We're not going to get super in depth, but we're going to hit some of the main vocabulary for it. So the objectives, when you've completed this chapter, you should be able to do the following. Describe the heat treatment theory. Identify the stages of heat treatment. Recognize heat treat colors associated with steels. We're not going to get too much into that. Describe the different types of heat treatment, and we're going to talk about a couple of the different quenching medium. Okay, so when we get into talking about metallurgy and heat treatment, it all gets back to carbon. And carbon's the most important alloying element in metallurgy of ferrous materials. Remember we talked about ferrous materials yesterday? We talked about carbon, and it causes the strength of the material to go up. So that's what we're looking at here. So, sorry about that, I got a dog here. It's an interstitial element, so that tells us that carbon plays a role, and it goes into the spaces in between the iron. So it helps to harden the material, and it also controls the maximum allowable, achievable hardness in the material. So what we're talking about when we're talking about physical metallurgy is we're talking with iron. Iron at room temperature is base-centered cubic. That's this guy up here in the corner, this BCC. That's base-centered cubic. When you heat iron up, it goes into a face-centered cubic situation, and all the atoms rearrange, and that's called a transformation temperature. So it goes through an allotropic phase transformation. So you can see we've got, it's body-centered cubic. If we heat it up, it goes to face-centered cubic. Here we've got hexagonal close pack, and that's just for materials like titanium and zirconium. They've got a different crystalline structure. We're not going to talk about that. The ones we're worried about are body-centered cubic and face-centered cubic. So when we're heating materials up, we're taking it from a body-centered cubic to a face-centered cubic, and then on the way down we might slow cool it. And so in a normal situation, your iron would go from a body-centered cubic to a face-centered cubic, back to a body-centered cubic structure. Well, if we go into like let's say we're making a sword like back in the old days, you'd take it from body-centered cubic to face-centered cubic and then you'd quench it and it would go to body-centered tetragonal. So that's what we've got over here, and that's what we're talking about when we're talking about martensite. So you can see that it's got a little different crystalline structure than body-centered cubic. So here we've got martensite. Martensite is formed by the rapid cooling and quenching of austenite, which traps carbon atoms that do not have time to diffuse out of the crystalline structure. The martensite reaction begins during cooling when the austenite reaches the martensite start temperature, and the parent austenite becomes mechanically unstable at a constant temperature below ms. A fraction of the parent austenite transforms rapidly. So what's going to happen is this thing is going to cool down, and it leaves some tension in. This is my version of it, but it leaves some tension in the material, so it makes it harder. So you're going to have carbon. So the more carbon you have in a material, the easier it is to get martensite to form. All right, so we're going to start out. I'm running off of, where are we at here? Basic heat treatment topics, and this is in U.S. Navy 14250, which is a Steelworker manual. So as you can see, yesterday or the other day we did introduction to types and identification of metals. Today we're going to do basic heat treatment, and then we'll work our way into introduction into metals. So all heat treatment processes are similar because they all involve heating and cooling of metals. That's what it boils down to. But there's differences in the metals, in the methods used, such as heating temperatures, cooling rates, quenching media, necessary to achieve the desired properties. So, hold on a second, I gotta get this dog out of here. Mike, come down here and watch this dog now. I'm not asking again. Joys of working at home dealing with the dog. Sorry, my apologies. So we're going to talk about heat treatment of ferrous materials, of iron, because that's the most popular material you're going to work with is irons and steels. So you're going to have to get familiar with annealing, normalizing, hardening, or tempering, quenching, some of this terminology. Most non-ferrous metals can be annealed but never tempered, normalized, or case hardened. And that's due to the fact that they don't have that mechanism of carbon in there in the interstitial sites, causing it to get harder and stronger. So, all right, where are we going next here? Next slide. Heat treatment equipment. You know, this is just telling you, if you're going to do heat treating of any sort, you should probably have the equipment. Everything for heating and cooling, you're going to need the size of the furnace, depending on what you got going on. A lot of times in welding, you're going to use, for post-weld heat treatment, you're going to have coils wrapped around a piece of tubing. There's going to be different equipment or a furnace. Depending if you're doing big castings or whatnot, you could be using a furnace. The furnace atmosphere is going to affect the material too, and what you've got going. So, I don't know. This whole thing is just killing me. I don't know if I'm still going or not, but I guess we'll keep plowing on. My bad. All right. To successfully, the furnace atmosphere is going to affect things. So that's why a lot of times in a fuel-fired furnace, you got to worry about the atmosphere. Mixture gases and air, the fuel's combustion. You can have various things going on in there. And I'm not an expert. I just know that you can put carbon monoxide in there, carbon dioxide, hydrogen, nitrogen, oxygen, water vapor, and other hydrocarbons to get the heat treatment that you want. And you can vary the proportion of air and fuel and fuel-fired furnaces to get what you want. So you can have oxidizing, reducing, and neutral atmospheres in a furnace to get what you want. All right, where's our next slide? Okay, so here's the big thing is when we talk about stages of heat treatment. So on stages of heat treatment, you're going to have a heating stage, you're going to have a soaking stage, and you're going to have a cooling stage. So your heating stage is how fast you're heating this thing up. We're taking it from, room temperature, let's call it 70 degrees up to 1,000 degrees. So you're going to have various rates on these heating stages. This is something that if you're ever sending something to a heat treat oven or the heat treater, you want to make sure and give them directions that say, hey, use this rate to 250 degrees per hour, because you don't want to just throw something from room temperature, especially if it's a thick piece of material. You don't want to just throw it in an oven and go from room temperature to 1,500 degrees in 30 minutes or whatever, because you'll just crack it or you're going to end up damaging the material. So that's what we talk about the heating stage, and we'll cover this in a little more detail. Soak is you hold the metal at a given temperature for a given time. So that's telling you how long you're cooking your pizza. How long you're letting it heat up or not heat up, but sit there and soak. It's like throwing something in a smoker or something, kind of how long it's in the oven. Make sure that the turkey is cooked all the way through, or whatever analogy you want to use. And then to cooling is the cooling stage, the cooling rate. How long does it take to cool this thing down to room temperature? That's what we're talking about when we're talking about the cooling stage. The heating stage. In the heating stage, the primary objective is to heat uniformly and attain and maintain uniform temperatures by slow heating. If you heat unevenly, one section can expand faster than another, resulting in distortion and cracked parts. So that's what you just got to be careful with this on the heating and bringing it up to temperature. This part down here where it talks about a metal size and cross section, that you really have to look at that no matter what you're heating, and give your heat treat people an idea of what temperatures you need to heat it at and what ramp up rate you want, so you don't crack this thing or damage it or warp it or whatever. So there's this whole heat treat thing. There's some, I want to say, some science in it, but it's also an art form. Whenever I dealt with heat treat people, I just give them, all right, don't do this. This is what I want. This is, heat it up to this temperature at this rate, and then hold it, and then quench it, or do whatever. But give them pretty good instructions helps. All right, let's go to stages of heat treatment. The heating stage. That's what it's going to look like if you had a time here on our x-axis, and y is our temperature. So it's just, your heating rate. How many degrees over what period of time? You know what I mean? Am I 100 degrees an hour, 500 degrees an hour? And then you're going to take it up to your soaking stage. In the soaking stage, the objective is to hold the metal at a proper temperature until the desired internal structural changes take place. It's like cooking a big piece of meat. You could burn the outside and the inside could be raw. The same thing could happen with a piece of material you're trying to heat treat. The chemical analysis of the metal and the mass of the part will determine the appropriate soaking period. You need to look this stuff up. There's a lot of good information out there on the internet that'll tell you the different, give you some guidance. There's also books out there, libraries of books. Except for rare variants, you should not bring the temperature of a metal directly from room temperature to soaking temperature in one operation. So you don't want to just blast it in there. That's what we were saying. You want to bring it up slowly. You want to gradually bring the temperature of the material that you're heat treating up slowly. And this is what it would look like. We've got our heating stage, soaking stage, and cooling stage. All right, now we're going to talk about the cooling stage. The cooling stage would be, example I always use would be like when you're watching them make a sword in the old movies and they just get it red hot, super red hot, and then they dunk it in the ice cold water or in the oil or whatever cooling medium they have. That's quenching. So in the cooling stage, the objective is self-explanatory, but there are different processes to return metal to room temperature depending on the type of metal. To cool the metal and attain the desired properties, you may need to place it in direct contact with a cooling medium, a gas, liquid, solid, or a combination thereof. So in the cooling stage, you might want to slow cool it or you might want to quench it. But I used quenching as an example. Sometimes you want to slow cool it, bring it down very slowly, maybe 100 degrees per hour. But other times you might want to quench it, go from whatever temperature you're at, a couple thousand degrees Fahrenheit down to nothing very quickly. And I mean nothing, I mean room temperature or lower. Cooling metal rapidly in air, oil, water, and brine or some other medium is called quenching. So that's what we're talking about there. So you just taking it from whatever your soaking temperature is down to room temperature, and you're doing it at a very quick rate. Obviously, you're not using, some materials, depending on the chemistry, can be air quenched, but some not. Quenching is usually associated with hardening, since most metals that are hardened are cooled rapidly during this process. However, neither quenching nor rapid cooling always results in increased hardness. For example, a water quench is usually used to anneal copper, and some other metals are cooled at a relatively slow rate for hardening, such as air-hardened steels. Some metals crack or warp during quenching, while others suffer no ill effects. So the quenching medium must fit the metal. You got to do your research on what's the proper material to use here for quenching. What's the medium you're going to use? Oil mixtures for metals that need slower cooling rates, water-hardened carbon steels, oil-hardened alloy steels, and quenched non-ferrous materials in water. Okay, we got basic types of heat treatment. We're going to talk about annealing, normalizing, hardening, and tempering. So what do we got here? We've got the objective of annealing is the opposite of hardening. To anneal metals, to relieve internal stresses, soften them, make them more ductile, and to refine the grain structures is what you're headed for. The process includes all three stages of heat treatment already covered. Heat the metal to a specific temperature, hold it at a temperature for a set length of time, cool it to room temperature. But the cooling method will depend on the metal and the properties desired. I used to work at a foundry out on the West Coast, and depending on what the material was, some material you could quench in air. It was air quenching. Other stuff, they'd take it out of an oven and drop it in a tank of quenchant, these quench tanks that are about the size of a swimming pool, and they'd throw this red hot chunk of metal in there and put it in there with a giant forklift, and it'd shoot water 30 feet in the air. It was pretty crazy to watch, but it all depended on the metallurgy, the metal that you were trying to cool down and what the end use was. So there's no one size fits all. I'm just using a few words here, and we're just kind of swimming in the shallow end of the pool. Annealing, under certain job conditions without proper preheating, welding can produce areas of molten metal adjacent to other areas at room temperature given specific conditions. Welding can actually weaken a metal as a weld cools, internal stresses occur along with hard spots and brittleness. So sometimes you need to anneal a weld. So sometimes, you're going to bring it up and to a certain temperature and anneal it. Ferrous metal annealing. To anneal ferrous metals and produce a maximum softness, the ductility in steel, you slowly heat the metal to its proper temperature, soak it, and then cool it very slowly by burying the hot part in insulating materials or by shutting off the furnace and allowing the furnace and the part to cool together slowly. So that's another option. A lot of times you'll send something and you'll tell them, okay, you can take it out of the furnace and just cool outside the furnace, or sometimes you want it cooled inside the furnace, really slow cool it. Or you can, sometimes they'll bury them in, hot piece, or like basically kitty litter, a granular material that'll, like sand or something, that'll hold the heat in the part, and it'll have a slow cooling effect. Soaking periods depend on both the type and the mass of the metal involved. There's a table in this book that give you approximate soaking periods for annealing steels of various thicknesses. Extremely low carbon steels require the highest annealing temperatures, but as steel's carbon content increases, its annealing temperature decreases. That's kind of, I guess, counterintuitive maybe, but I guess it's how it works. Full annealing is done to soften a metal to make it more ductile and to relieve stress. Internal stresses caused by the previous treatment, such as casting, cold working, or hot working. The operation known as process annealing or stress relief annealing is done to soften the metal to somewhat, though not as much, by a full annealing and to relieve internal stresses. Non-ferrous metals. These may or may not follow the same process as ferrous metals. Copper becomes hard and brittle when mechanically worked, but it can be made soft again by annealing at a temperature between 7 and 900 F. However, copper may be cooled rapidly, normally associated with hardening, or slowly, since the cooling rate has no effect on the heat treatment. So you can cool copper down quickly and it's not going to affect the hardness. It doesn't have the same mechanisms for hardening that steel does with the carbon in there. Okay, so this is what normalizing would look like. The intent of normalizing is to remove internal stresses that may have been induced by heat treatment, welding, casting, whatever. So sometimes you'll run across this normalizing. And if you don't relieve these stresses, it'll cause failure. So normalizing applies to ferrous metals only. You can't do this with aluminum or other materials. The metal's heated to a higher temperature, but then it is removed from the furnace for air cooling. Low carbon steels do not require normalizing, but if they are normalized, no harmful effects. Castings are usually annealed rather than normalized. However, some castings require normalizing. Okay, so the purpose of hardening is not only to harden the steel, as the name implies, but it's also increase the strength. Like a quenched and tempered steel, or using materials that are like a knife blade or something. This goes back to Metallurgy 101 when our ancestors were making iron knives and the first steel swords and going down that road, making tools. But so when you make it harder, it's less ductile, and the brittleness, you'll get a brittle material, and like a knife blade or something, it'll shatter. So you need to temper it to after you harden it to put some ductility back in the material. Many non-ferrous metals can be hardened and their strength increased by controlled heating and rapid cooling. But for non-ferrous metals, the same process is called heat treatment rather than hardening. Most steel's hardening consists of employing the typical first two stages of heat treatment, slowly heat to the temperature, and soak time and temperature, but the third stage is dissimilar. With hardening, you rapidly cool the metal by plunging it into oil, water. This is quenching. Hardening of ferrous materials. The cooling rate required to produce hardness decreases when alloys are added to steel. This is advantageous since a slower cooling rate also lessens the danger of cracking and warping. So as you add other alloys to a steel, it's going to give you different cooling rates and different signature or fingerprint in regards to how it's cooling and what's going on with it. The following provides hardening characteristics for a few irons and low carbon steels. Pure iron, wrought iron, and extremely low carbon steels. Very little hardening properties. They're difficult to harden by heat treatment. So if you've got a really, really low carbon steel, you can't harden it. We did this in college when I was in university. The instructor gave us a piece of, what was it? Like really low carbon rebar material. And he tried to, we heated it up to, a couple thousand degrees in the furnace, then threw it in some water and tried to get it to cool down quick enough to get martensite to form, and you just couldn't get it. You couldn't get any, it just didn't work. Cast iron is going to be harder than heck anyway, so there's limited capabilities for hardening. Cooled rapidly, it's going to form white iron, which is hard and brittle. Cooled slowly, it forms gray iron. Slowly, it forms gray iron, soft but brittle under impact. So cast iron, can be heat treated too, depending on what you want with it. Plain carbon steel, it just depends on how much carbon content you've got in there. It gets back to the carbon of the material. Carbon is going to take up those interstitial sites, and the more carbon you have, the more martensite you can form when cooling the material. Hardening ability increases as carbon content increases to a maximum of 0.8% carbon. Let's fix that one while we're at it. Increased carbon content beyond 0.8 increases wear resistance but not hardness. So it's just going to get to a certain hardness, and then you're just not going to be able to get any more hardness out. That's it. You're just going to get more wear resistance. The increased wear resistance is from the production of hard cementite. And I'm not going to get that deep into this, but you can add other materials too, and I'm not sure all of these, but I'm pretty sure all of these can, vanadium. Adding an alloy to steel increases its hardness, also increases the carbon's effectiveness to harden and strengthen. Consequently, the carbon content required to produce maximum hardness is lower in alloyed steels than it is for plain carbon steels, with the result that alloy steels are usually superior to carbon steels. So you get some hardness and some other strength-related benefits. I mean, that's why they throw vanadium in tool steels or wrenches and tungsten, and it's not just plain carbon steel. They throw other alloys into tool steels and these types of materials to give them material properties that are greatly superior to carbon steels. When you harden a carbon steel, you must cool a steel to below 1,000 in less than 1 second. So you got to go from a couple thousand degrees down to less than 1,000 degrees in less than 1 second. When you add alloys to steel and increase the carbon's effectiveness, you also increase the time limit, more than 1 second to drop below 100. So then you can use different quenching medium to produce the desired hardnesses. You usually quench carbon steel in brine or water and alloy steels in oil. Tempering. After hardening by either case or flame, steel is often harder than needed and too brittle for most practical purposes, containing severe internal stresses that were set up during the rapid cooling. That gets back to our previous slide when we talked about, let's go back to this guy. When you're going from body-centered cubic, well, realistically, you're just going from when you're at this phase, you're at face-centered cubic when you're in your soaking phase, and then you're going to go, remember they said you wanted to go from here to here in less than a second. You wanted to go to this body-centered tetragonal. So you want to go from here, you want to go from body-centered or face-centered cubic, which is the middle one that I'm showing the pointer on, over to this guy in less than a second. But when you do that, you're going to throw a lot of stresses into the part. A lot of internal stresses that are not going to be good for the long-term health of that part. So that's why we have tempering, to get rid of these severe internal stresses. Tempering consists of heating the steel to a specific temperature below its hardening temperature. So you're going to heat it to a specific temperature, and then you're going to hold it at that temperature for a required length of time, cooling it usually in still air. So this diagram kind of shows you what we've got when we're going to temper something. So we take it up to our austenizing temperature and our soak temperature up here. We'd soak it and then we're going to quench it. We slam it, and it's got to go from, a couple thousand degrees to down below 1,000 degrees in less than a second. Well, then we're going to keep it at that temperature for a while, whatever that temperature is. Maybe it's 100, 200, 300 degrees. We're going to keep it at that temperature for a while to let that, let it stabilize, I guess is what I'm looking for. Then we're going to heat it back up, and then we're going to do our tempering. When we do tempering, we don't take it back up to as high as we did when we were, before we quenched it. We're just taking it up to, let's say, 900, 1,000, 1,100 degrees Fahrenheit. And if you're listening and you're a Celsius guy, I'm sorry. I can't think in Celsius. But you're just going to take it up, and you're going to let it, it's going to soften. It's going to take a little bit of the stress out of the material. And that's what we're talking about when we're tempering. And then once you hit that time, you bring it down. You usually let it slow cool, and you should have a structure in that material that's got a heck of a lot less internal stresses in it. Okay, so you're going to temper a part to reduce the brittleness. And the brittleness is caused by hardening. It gets back to that mechanism with where we had, when we went from face-centered cubic to body-centered tetragonal for carbon steels, right? Because you got the carbon in there, and it's taking up the interstitial sites. It also softens the steel. So you're going to, it's always a fine dance with steels on whether you're going to, is it going to be too hard, too soft? Is it going to be strong enough? Is it not going to be strong enough? So a lot of times with this tempering and, heat treating, you're trying to hit a pretty narrow window for, your material properties. I want this tensile strength, but I don't want it to be too hard and too brittle. So that's what we're looking at there, and why where we're headed with it. The annealing, normalizing, and hardening process all include steps at temperatures above the metal's upper critical point. Tempering is always conducted at temperatures below the low critical point. So you don't go, without getting too much into it, if you look at this, right in here, see if we can, so all this stuff would be above like the upper critical, and then you've got a lower critical temperature, and this has to do with the way the metals and everything work. I'm sure there's a second temperature here. Tempering always happens below these two, so you don't have any change in structure. You're just stress relieving it. So that's where we're down to here. The annealing, normalizing, and hardening processes all include steps at temperatures above the metal's upper critical point. Tempering is always conducted at a temperature below the metal's lower critical point. Yeah, we just did that one. Tempering relieves internal stresses from quenching. It reduces hardness, brittleness, and may actually increase the tensile strength of hardened steels that is tempered up to a temperature of about 450. Above 450, tensile strength starts to decrease. Typically, tempering increases softness, ductility, malleability, and impact resistance. But again, high-speed steel is an exception to the rule. We're not going to talk about that too much. If you're tempering a part properly, you need to remove it from the quench bath before it is completely cold. Proceed with the tempering process. Quenching media. There's a lot of different quenching media that you can use. I'm not going to get into all of those. You can use salts, you can use water, you can use air, you can use different oils. The mass of the part's going to affect the quenching. The greater the mass, the greater the time required for complete cooling. Configuration of the part. Parts may have the same size, but holes and recesses cool more rapidly than solid objects, so this is something that you need to look at. This is what you're talking about quenching. Quenching is, if we're up here at our soak temperature up here, and then you just, how fast can we cool this thing down? It's the cooling of a metal from an elevated temperature. The quenching media may be water, oil, forced air, synthetic quenchant. Composition of the part. The chemistry of the part is going to decide what your cooling rate is, and without cracking or warping it. The initial temperature of the part. Different steels and different steel alloys require a wide range of temperatures for heat treatment. Final properties desired. The medium must cool the metal at the rate you need, so rapidly or slowly. And I saw, let me see if I can go find it again. In here there was a kind of a cool looking chart that told you quenching mediums. So here's properties of average cooling abilities. So this is compared with water. You can see caustic soda in here. It's going to quench about 2.06 times as fast as water. Brine, I didn't realize it was twice as good as water. That's interesting. Brine, 10% at 65 degrees is going to be twice as good a coolant as just regular water. Here's water, that's our baseline.
It's the end of the world.
And then you've got prepared oils, fuel oils. You got a bunch of different, castor oil, machine oil, lard oil. Lard oil, if you had a chunk of lard. Circulated air. You can see circulated air doesn't quench nearly as well as water does, and still air. Where are we at here? Liquid quenching. There are two methods for liquid quenching. A still bath. Metal is cooled in a tank of liquid. Only movement of the liquid is caused by the movement of the hot metal, so you're just dunking it in there. The other one is flush quenching, where you've got just sprayed onto the surface and uniform cooling. A lot of times, that place I worked out in on the West Coast, they had these big tanks and pumps, just giant pumps for circulating and making sure that the liquid was at the right temperature, and just you got uniform cooling of the part. So it was a pretty complicated evolution. As far as it wasn't, because you're throwing parts in there that are the size of a Volkswagen, and it's, pretty good. Well, I'll show you that picture too. This picture, you've got it says commercial polymer quench tank. I don't know what the cooling medium is, but that looks like some kind of big axle or something. And they're taking it in there. That thing's glowing red hot, and they're chunking it in there. So, and then you've got, we talked about martensite, but you know, this would be like a portable quench tank where you got oil and water for if you're doing stuff that's like, what am I going to say? You know, making swords or hand type instruments or whatever, or maybe you're taking something out of the oven. So, we covered a few of the elements of heat treatment theory, explained how you can change the properties of metals. I didn't get super into it, but I'm just on my mission to cover this material. I started at chapter 1, so chapter 1 and chapter 2 I probably went over a little lighter than I'm going to go over the welding processes because I'm not a super metallurgist. I can kind of talk to those people, but it's not really my game. But I do know where to look it up. Anyways, thanks again for watching. If you get a chance, visit our website. We got a CWI course, Part A. Part B, we're working on getting Part C for AWSD 1.1. We've got a bunch of PDH hours on there that are relatively cheap for mechanical engineering. Check out some of the options if you need PDH hours. Anyways, thanks for watching. Have a nice day, and sorry for the dog. Kind of happens when you're working at home. So anyways, take care, and thanks for watching. Stay safe.